It is section 15.3, other variational principles for FEMs. In the last section, you studied core concepts of FEMs. There were 4 steps. In the beginning, you start with a partitioning of the given domain. Secondly, you introduce a subspace, and along with basis functions, the unknowns are recognized. In the third step, by using variational principle, you can get equations. And we did along with weighted residual approach, which is the Collocation method. And the last step, you'll do assembly for an algebraic system. So far, we have considered the Collocation method. Now, here, we'll consider other variational principles. So it's about the third step, not completely independent from other steps. However, it's mostly about the third step, other kinds of the third step. Here we have some principles. Start with a minimization principle, which is called the Rayleigh-Ritz method, and least squares approaches, and collocation method. And also, for weighted residual approaches, you may try to choose some the trial functions, the test functions, or weights different from the basis functions. So one example is Petrov-Collocation methods. We'll try to cover these 3 variational principles. Let's begin with the Rayleigh-Ritz method. Once basis functions are determined from the second step, the approximate solution U sub h can be formulated in this way as a linear combination of basis functions. Now, unknowns are psi j. The Rayleigh-Ritz method is trying to find an approximate solution of that equation which satisfies that one, so that for the linear functional, here we try to find the minimizer. And earlier, the differential problem and variation problem and minimization problems are equivalent under certain conditions. Now that minimization problem is along with this functional. Now we try to find the minimizer of the functional. Okay. In detail, we can write in this way. And once we are using now U sub h for the position V, then we reach that one. Now, U sub h is the minimizer, so that once we try to get the derivative, then along with the parameter, then the derivative must be 0. So along with the derivative technique, we can get the normal equation. Here we start the differentiation. For each unknown, we try to make a derivative. Okay, in detail, you can easily check that for psi I direction, you can reach that, and these 2 terms equal 0, so we can reach at this one. Now, this one is exactly the same as the result from the Collocation method, so that we can write in this way by using the definition we earlier considered. and again define Aij to be that we did in the last section for the collocation method, and Bi we define this way. So eventually we can get the same linear system. Okay, that is the Rayleigh-Ritz method. For this problem, it's the same. Okay, let's see this note. The resulting linear system of the Rayleigh-Ritz method is the same as that of the collocation method. In general, these two methods are the same for linear partial differential equations. However, if we consider a little more general differential equations, then they are not the same. Anyway, here the key point is the Rayleigh-Ritz method is trying to minimize the minimization problem. Now, we'll see second other method is based on least squares approach. Here we defined this operator Pu, that is from the differential equation we have that. Now also for the residual, and we earlier defined this one, and now for the true solution, residual must be 0. However, for the approximation, the approximated solution U sub H, the residual is not 0 in general. So that in this least squares FEM, we try to minimize just this residual squared. So it's called the least squares FEM. Now that residual squared is minimized, and the minimizer is the solution. In this way, the method is trying to find the approximate solution. Now, once U sub H is found, then at the moment, the derivative with respect to the parameters, the unknowns, must be 0 from calculus. Okay, so once we try to differentiate the integral equation, then we reach at this one. Of course, here W is derivative of R with respect to psi I. So we can reach at this operator P is the original PD operator here, differential operator. Okay, so the least squares FEM can be formulated in this way. Now, not often happening. However, anyway, once we are using integrals by parts, then we can reach at this formula, which means that now for weight is using this whole thing and along with differentiation. So rather than the basis function as in the collocation method, so way more complicated, the weight function is now being used here. So in order to simulate by using this technique, and your basis function must be higher order. After differentiation, if it disappears like a linear, the polynomial, then you cannot get really the solution effectively. So your basis function must be higher order polynomial. The degree must be high enough so that you can get the solution reasonably. Okay, now we'll go to the collocation method. Collocation method can be seen as a part of weighted residual method. Now, the weights are chosen from the evaluation function, direct delta function. So once W is chosen x minus xi, delta x minus xi, that means that we are evaluating this one at xi. So here, so for the integration from 0 to 1, this is the integrand, and delta x minus xi is there, then that one must be for this function just the evaluation at xi. So the collocation method will make, okay, residual is defined to be here the differential operator minus right side f, so that after evaluation we can move this one to the other side. Then that's exactly now this one. So for the differential operator, we are evaluating at xi. Of course, okay, right now, I guess I forgot here, there must be psi j. I forgot this one, sorry. Yes, typo. And over there, psi j must be there. Okay. Now, so that we can make here, if you choose the I point, I is from 1 to m points, and you can get m equations. And this one has originally m unknowns. So carefully choose the collocation points so that you can get n equations having n unknowns. So you can solve the problem. And that means you can find the unknown values, psi j. Much attention in the literature has been given to the choice of the Bessel functions and collocation points. One popular choice is that psi j are cubic B-splines and xi are Gaussian points. Okay, we solved this problem by using the Gallatin method. Now we'll see again this problem. Now here we'll try to solve by using collocation method. And P is x plus 1. The domain is from 0 to 1, so that is positive. And we have this x star 1. And then now here right side is made so that the exact solution is here. Find the numerical solutions using the collocation method. Now let's choose these three basis functions. And x minus 1 is phi 1. Okay, again, I made a mistake here. There must be 1. And phi 2, that's x squared x minus 1. And phi 3 is now given in this way. The problem has, the solution has function value 0 at the both sides, the edge points. So I chose the Bessel functions having the same property. So I chose these three polynomials, and I chose the collocation points here, 1/4, half, and 3/4. So we may get 3 by 3 system, and after solving it, we can find the solution. Now the code is in Python. By using symbolic tool, we can get differentiation, because here you have to get this differentiation, and then you have to evaluate after differentiation at the collocation points. So that's reason. Now I try to choose use the Python symbolic tool. Okay, here, and start with Okay, start with from now simply, and symbols are open, and that is P and Q, and now there is right side, there is a true solution, and phi 1, phi 2, phi 3, and our U sub H, the approximate solution, is linear combination of the basis functions. Now, we have to get P UH, P of UH, that is through symbolic differentiation, we can get it. Okay. Now, after getting it, and for 3 collocation points, we try to now evaluate and make the, here, that is now the each iteration. For each point, we are making one row of the algebraic system, and after passing this one, we have now algebraic system. Okay, so we can solve it, and the bottom portion is plotting. Okay, here, that is P of UH. Is a bit complicated. After simplification, we reach out this one. Now that is AB, and for each point is one row is made, and then now here, and along with this one, we can get the solution. In fact, and I attached also B over there, and after finding the unknowns, psi 1, psi 2, psi 3, and here put, now substitute, okay, this value is here, now that one is here, and this one is here. Now, in this way, we get U sub H, and now plot is made. The blue one is exact solution, and the red one is the collocation solution. And if you choose one high order polynomial, then you may get really quite accurate solution. Along with the 3 basis functions, the collocation method found this solution. Red curve is reasonably good, right? Okay, this is the end of the section. Thank you.